Now, as we look at the impact of adding carbon dioxide to the atmosphere and the massive amounts that we are today by burning fossil fuels, and we look at the sensitivity of climate to that increase in carbon dioxide, and we look quantitatively at the irreversible changes that are taking place to the climate system, it becomes immediately apparent to us that two things are required. One is that we have to terminate as soon as possible the release of CO2 and methane into the atmosphere. But the second thing we need to do is to draw carbon dioxide back down from its current levels to the levels that establish a stable climate structure. And we only have a stable climate structure if we have the ice systems in place in both the Arctic and the Antarctic, because it's the delicacy of those ice systems that determine the overall structure of the climate. So in order to extract carbon dioxide from the atmosphere, we have to do this actively. And so that opens up the subject of case study 6.2. It's called Direct Air Capture of Carbon Dioxide. And this is rapidly emerging as a very important industry. And what it does is that it takes carbon dioxide at 400 parts per million. It passes it through the system that we'll describe in just a moment to reduce this to something on the order of 300 to 250 parts per million of CO2. So how is this done? What is the chemical and mechanical technique for actually extracting CO2 from the atmosphere? So there are a number of different ways of doing this. We're going to point out just one of them here, and that is that we're going to move air into an exchange process that takes sodium hydroxide, reacts it with CO2 to form sodium carbonate. That sodium carbonate is passed through a system, and heat is added to the system to break sodium carbonate into an intermediary chemical compound that in this case is sodium, iron, and oxygen. And that reaction with water turns out to reform sodium hydroxide. So sodium hydroxide is then fed back into the system. So the energy required to execute the extraction of CO2 comes in the form of the heat that's necessary to add this. Now this is a very interesting region or area of research currently going on, because this can be done by the direct application of heat, but it can also be done through electrochemistry. And Chapter 7 will tell us how we can execute this in the most efficient way possible, consuming the least amount of energy. But it's also clear that the energy that goes into the extraction of carbon dioxide has to come from renewables in order for a net extraction of carbon dioxide to take place. So when we look at the mechanical system that's evolved in this extraction, these mechanical systems are very impressive. So we want to point out the scale of a human being here, and what's required are these fan systems that draw carbon dioxide rich air in and focus the flow of that carbon dioxide into the chemical reactor so that out of the backside comes air depleted in CO2. So these arrays are comparable in size to very large buildings. And then, of course, the immediate question is that, well, you've extracted CO2. Now, what do you do with that CO2? And that's an entirely different and very interesting topic, which is called carbon capture and sequestration. That is, we can pump carbon dioxide down into particular chemical environments below the Earth's surface, and it will permanently react to form a stable product. We can also bury carbon dioxide in the bottom of the ocean, where the temperatures are very low and the pressure is very high, and that provides a thermodynamically stable sink into which we can inject carbon dioxide, and it will stay as that injected quantity below the bottom of the ocean.